Hi students, welcome to physics class. Make sure that you have watched the previous videos, and today I am going to teach Stokes Law from the unit Properties of Matter. The scientist Stokes has performed many experiments on the motion of small spherical bodies on different fluids. At last he concluded the viscous force acting on that spherical body. When a body falls through a viscous liquid, there will be a relative motion between the different layers of the liquid. That is, it drags the layer of the fluid immediately in contact with it. The spherical body or the object, it drags the layer of the fluid immediately in contact with it. So he has done many experiments and he concluded the viscous force. The viscous force F acting on a spherical body of radius r depends on radius of the sphere or velocity of the sphere v and coefficient of viscosity eta of the liquid. Viscous force F acting on a spherical body of radius r depends on radius of the sphere r, velocity of the sphere v and coefficient of viscosity eta of the liquid. So I can write the force F proportional to eta or v. This we can written as F proportional to eta power x, r power y, v power z. So the powers of these radius, velocity and coefficient of viscosity we don't know. That we are going to obtain from the dimension analysis. So we can write F proportional to eta power x, r power y and v power z. The proportionality can be removed by using a constant called k. So F is equal to k eta power x, r power y and v power z. Now apply the dimensional formulas on each sides. So we know that k is a dimensionless constant. It is a constant and it has no dimension. Dimensionless constant. What is the dimension formula for force? Yes, for force the dimensional formula is m L t raised to minus 2 mass into acceleration. Then dimensional formula for the coefficient of viscosity. In the previous class I explained. Just go through that. That is m L power minus 1 t power minus 1. Next, the radius. What is the dimensional formula? It is nothing but distance, so L. Velocity. What is the dimensional formula? L t power minus 1. So substitute this dimensional formula in this equation and solving that equations we will get the powers x, y, z. So we can write m L t power minus 2, that is force is equal to k. There is no dimension, so we don't want to use. And eta m L power minus 1 t power minus 1 the whole power x and L power y and L t power minus 1 the whole power z. Now compare the powers of m, L, t on both sides. We can solve the x value, y value and z value. So before that we can write m power x, L power minus 1 into x minus x and y is there and z is there. So L power minus x plus y and plus z. Then t power minus x then minus z. So m L t raised to minus 2. Now if you equate the power on both sides, equate the power of m. So, x is equal to 1. X is equal to 1. Then minus x plus y plus z is equal to 1. Next, minus x minus z is equal to minus 2. So, x equal to 1 we have got. If we substitute x equal to 1 in this equation, what is the answer? Minus 1 minus z is equal to minus 2. So, if the 2 comes this side, minus 1 plus 2 is equal to z. So, z is equal to 1. So, x is equal to 1 and z is equal to 1. Substitute this value in this equation. Minus x plus y plus z is equal to 1. Minus x plus y plus z is equal to 1. X is equal to 1 minus 1 plus y, z is equal to 1 plus 1 equal to 1. So, minus 1, 1 gets cancelled. So, y is equal to 1. So, we got the values are x is equal to 1, y is equal to 1 and z is equal to 1. When we substitute these values in the equation, we got the expression f is equal to k into eta power 1, r power 1 and b power 1. The k value found by Stokes as experimentally, k is equal to 6 pi. So, f is equal to 6 pi eta rv. This relation is known as Stokes law. The Stokes law in the previous terminal velocity explanation also we have used. Isn't it? So, Stokes law, Stokes performed the experiments by means of different spherical balls falling on different viscous liquids. And he concluded the forces, force depends on the radius of the sphere, force depends on the velocity of the sphere and force depends on the coefficient of viscosity of the liquid. Then he find out the equation, that is f proportional to eta rv, f is equal to k into eta power x, r power y, v power z. Then we have to substitute all the dimensional formulas and simplify that. Equate the power on both sides, m power, l power and t power. We will get x equal to 1, y equal to 1 and z is equal to 1. On solving that, we will get f is equal to 6 pi eta rv. It's a very important question. Stokes law. Some practical applications of Stokes law is given in your book. That is, raindrops are smaller in size and their terminal velocities are smaller. It remains suspended in air in the form of clouds. As they grow up in size, their terminal velocities also increase and they start falling in the form of rain. So, this law explains the following, that is, flotation of clouds. Flotation of clouds. Larger raindrops hurt us more than the smaller ones because the force is proportional to velocity as well as coefficient of viscosity as well as the radius. Okay. So, this law explains the following. Flotation of clouds. Larger raindrops hurt us more than the smaller ones. A man coming down with the help of a parachute across the constant terminal velocity. The next one is Poisseless equation. This is one of the most important question. The scientist Poiseuille find an equation for the volume of the liquid flowing per second. Volume of the liquid flowing per second through a capillary tube. Actually, he has analyzed the steady flow of liquid through a capillary tube. Okay, analyze the steady flow of liquid through a capillary tube. And he got the expression, the equation for volume of the liquid. Volume of the liquid flowing per second. volume of the liquid flowing per second. So as per his theory, he has a important conditions. First condition is the flow of liquid through the tube should be streamlined. He got the expression by means of these assumptions, that is the conditions. The flow of liquid through the tube is streamlined. Second one, the tube is horizontal. The tube is horizontal so that gravity does not influence the flow. Third point, the layer in contact with the wall of the tube is at rest. The layer in contact with the tube is at rest, and the pressure is uniform over a cross section of the tube. Pressure is uniform. Okay. So the following conditions must be retained while deriving the equations. What are these conditions? The flow of liquid through a tube should be streamlined, and the tube should be horizontal so that the gravity will not affect, and the layer in contact with the tube, the wall of the tube is at rest, and the pressure is uniform over any cross section of the tube. Now let's see the derivation of the Poissel's equation by means of dimensional analysis. Alright. So consider liquid steady flow liquid through a horizontal tube. Here the volume V is equal to, actually we are going to find the volume of the liquid, volume of the flowing liquid per second. So I can write V is equal to V by T, the volume of the liquid flowing per second. So V is equal to V by T. So this depends on coefficient of viscosity eta, coefficient of viscosity eta of the liquid. Then it depends on the radius of the tube, R, and it depends upon the pressure gradient. Pressure gradient, that is P by L. When the gradient word comes, we should divide with the help of a distance or length. Okay. So the volume of the liquid flowing per second through a capillary tube depends upon coefficient of viscosity eta of the liquid, radius of the tube R, and the pressure gradient P by L. Now, as like Stokes law, we can write the equation as this V proportional to eta power x, R power B, P by L power C, A, B, C. Okay. So, eta power A, R power B, P by L power C. Understand? And it can be written as V is equal to a dimensionless constant K into eta power A, R power B, and P by L the whole power C. So, obviously we know that K is a dimensionless constant, isn't it? K has no dimension. K has no dimension, and the other dimensional formulas we have to substitute, and by solving that we will get the power ABC, then we will get the Poissel's equation. Let's see. So, the volume dimensional formula, actually the dimension formula for volume per second, isn't it? So, how will you write? L cube T raised to minus 1. L cube T raised to minus 1. Volume of the liquid flowing per second. And eta. Eta we know that. What's that? M L power minus 1 T power minus 1. Then R L alone. Now pressure gradient. that is P by L, isn't it? P by L, or we can say dP by dx, change of pressure with the distance. So, dP by dx, it can be written as, what is the formula, dimensional formula for pressure? M L power minus 1 T power minus 2 divided by dimensional formula for distance is L. So, we can write it as M L power minus 2 and T power minus 2. So, these are the dimensional formulas. For V, L cube T raised to minus 1. For eta, M L power minus 1 T power minus 1. For pressure gradient, P by L is equal to M L power minus 2 and T power minus 2. Then R L. Let's substitute this dimensional formula in this equation and solve that equations. So, for volume, L cube T raised to minus 1 and proportional to K has no dimension, then eta M L power minus 1 T power minus 1 the whole power A, then R L power B, then pressure gradient M L power minus 2 T power minus 2 the whole power C. Let's simplify this. Here there is no power on M, so we can write M power 0 L cube T raised to minus 1. That is equal to, here M power A plus C, right? A, then here there is no M, here yes. So, M power A plus C, then L power minus A plus B and minus 2C, minus A plus B and minus 2C, then T power minus A minus 2C, minus A minus 2C. So, when we are equating the power on both sides, we will get the equation as, for equating the power of M on both sides, A plus C is equal to 0, A plus C is equal to 0. So, A is equal to minus C, isn't it? A is equal to minus C. Then minus A plus B minus 2C is equal to 3. Minus A plus B minus 2C is equal to 3. Then minus A minus 2C is equal to minus 1. Minus A minus 2C is equal to minus 1. So, we can solve the equations. Let's consider this as equation 1, equation 2 and equation 3. We can easily solve the equation 1 and 2, 1 and 3, isn't it? So, A plus C is equal to 0, minus A minus 2C is equal to minus 1. When we are adding, this will be getting cancelled. So, minus 2C plus C, minus C is equal to minus 1. So, C is equal to 1. Already we got A is equal to minus C. So, if C is equal to 1, A is equal to what? Minus 1. Now, B, substitute A equal to 1 and C equal, A equal to minus 1, C equal to 1 in this equation, that is minus A. So, minus of minus A. So, minus of minus 1 plus B minus 2 into C. C is 1 equal to 3. So, 1 plus B minus 2 is equal to 3. So, minus 2 plus 1 minus 1 plus B is equal to 3. So, B is equal to 3 plus 1, that is 4. So, we got A is equal to minus 1, B is equal to 4 and C is equal to 1. Understand? So, when we substitute this equation, this powers on that equation, we will get V is equal to K. So, K into eta power A. A is minus 1, eta power minus 1, R power B, R power 4 and P by L the whole power C. C is 1. Okay. So, this can be written as, the experimentally the value of K is found to be pi by 8. Pi by 8. So, V can be written as pi by 8 into eta power minus 1, that we can write in the denominator, and r power 4 numerator, then P by L. So, this is Poisler's equation. V is equal to pi r power 4 P divided by 8 eta into L. This equation is known as Poisler's equation for the flow of liquid in the capillary tube. Okay, and keep it in mind, this relation is good for the fluids whose velocities are lesser than the critical velocities. This equation is holds for only the fluids which has the velocities are lesser than the critical velocity. Once again, so Poisler's equation is used to find the volume of flow of liquid per second through a capillary tube, isn't it? So V is equal to V by T and coefficient of viscosity. This V by T depends upon coefficient of viscosity, radius, pressure gradient, and note down the equation V proportional to eta power A r power B P by L the whole power C, and proportionality constant K eta power A r power B P by L the whole power C. Just write down the dimensional formula for all. V, keep it in mind, volume divided by time. Okay, so L cube raised to minus 1 and eta R, then P by L. On solving the dimensional formula, we will get A plus C equal to 0, A equal to minus C. So, on solving 1 and 3, we will get minus C equal to minus 1, C is equal to 1, A equal to minus 1, B equal to 4. So, we got the expression as V is equal to K is pi by 8, pi r power 4 P by 8 eta into L. So, this is known as Poisler's equation. Very important question. Listen, some of the applications of viscosity is given in your book. Actually, we are learning the viscosity topic, isn't it? In viscosity, coefficient of viscosity, cause of viscosity, types of flow, streamlined flow, turbulent flow, Reynolds number, terminal velocity, and today we have discussed about Stokes Law, Poisler's equation, isn't it? So, applications of viscosity. The importance of viscosity can be understood from the following examples. The oil used as lubricant for heavy machinery parts should have a high viscous coefficient. So, when we select a machine for oil for lubricant purpose, for heavy machinery parts, we use high viscous coefficient. Okay, for heavy machinery parts, we use high viscous coefficient. To select a suitable lubricant, we should know its viscosity and how it varies with the temperature. As the temperature increases, the viscosity of the liquid decreases. As the temperature increases, the viscosity of the liquid decreases. Also, it helps to choose oils with low viscosity used in car engines, light machinery. So, for heavy machinery, we use high viscous liquid, and for light machinery, we should use low viscous liquid. And the temperature increases, the viscosity decreases. Keep it in mind. Second point, the highly viscous liquid is used to damp the motion of some instruments and is used as brake oil in hydraulic brakes. Hydraulic brakes, they are using viscous liquid. That viscous liquid nature should be very high. Highly viscous liquid is used to damp the motion of some instruments. It is used for the brake application. So, it is used to damp the motion of some instruments and is used as brake oil in the hydraulic brakes. Blood circulation through arteries and veins depends upon the viscosity of the fluids. Okay, blood circulation depends upon the viscosity of the fluid through arteries. Millikan conducted the oil drop experiment to determine the charge of electron. He used the knowledge of viscosity to determine the charge. Okay, so this is about applications of viscosity. I hope you have understood today's class, especially Stokes Law and its applications, then Poisler's equations, its derivation and applications of viscosity. So, today Write down the expression for the Stokes force and explain the symbols involved it. This question we have discussed. And long answer, derive the Poisler's formula of volume of liquid flowing per second through a pipe under streamlined. So these two questions learn. Thank you, students.